You ever stop and think about what's really going on inside your computer? You've got web pages open, music playing, notifications popping up, all at the same time? Well, the magic behind all of that is the operating system. So let's dive in and figure out what this incredibly important piece of software actually does.
To get our heads around this, we're going to start with a really simple analogy. I want you to picture your entire computer, all the hardware, all the software, as one big, busy company. And right in the middle of it all, making sure nothing catches on fire, is a single crucial figure.
So in this company, your hardware, that's the CPU, the memory, the storage, those are your workers, your machines, and your tools. Your applications, your web browser, your games, your text editor, those are all the different projects that need to get done. And the operating system? Well, that's the manager. Its job is to tell the workers what to do, give them the resources they need, and make sure all the projects are running smoothly without getting in each other's way.
All right, so the first big problem for our manager is this. How do you handle a totally overwhelming number of projects? You might only have a few actual workers, your CPU cores, but you've got thousands of little tasks all screaming for attention at the same time. How on earth does it manage?
I mean, just think about your computer's to-do list right now. You've probably got a bunch of browser tabs open, maybe some music streaming, an antivirus program is doing its thing in the background, your system is checking for updates, and you've got messaging apps ready to ping. It feels like it's all happening at the exact same moment. But again, you might only have a handful of CPU cores to do all that work. So what's the trick? How does the OS create this incredibly convincing illusion that everything is running at once? Well, the secret lies in a very, very clever technique that our OS manager uses. It's all thanks to something called the scheduler. You can think of this as a hyperactive micromanager. It grabs a task, gives it a tiny, tiny fraction of a second on the CPU, we're talking millionths of a second, and then, boom, it switches to the next task and the next and the next. It cycles through them so incredibly fast that from our perspective, it feels completely seamless. And this is a great way to picture that workflow. See, the scheduler lines up all the tasks that are ready to go in this ready queue. It picks one, sends it to the CPU for its little time slice. Now, if that task needs to wait for something, like, say, a file from the hard drive, the scheduler doesn't just sit there. It immediately moves that task to a waiting area and grabs the very next one in line. It's this constant, lightning-fast loop of processing and prioritizing that creates the magic of multitasking.
Okay, so that's multitasking sorted. Next up for our manager, organizing the company's workspace. And in a computer, that's the memory, or RAM. Every project needs space to work, but you can't just let them spread out and mess with each other's stuff.
The OS has this brilliant trick up its sleeve called virtual memory. What it does is it gives every single application its own private, secure little bubble of memory. From the app's point of view, it thinks it has the entire computer's memory all to itself. It has no clue that your web browser is running in the bubble right next door. And this separation is absolutely crucial for a couple of really big reasons. First, security. It's what stops a shady program from peeking into the memory of your password manager. Second, and just as important, is stability. If one application crashes inside its own little bubble, it doesn't take the whole system down with it. The OS can just shut down that one process and everything else just keeps on chugging along.
All right, job number 3 for our OS manager, acting as the universal translator and, more importantly, the gatekeeper between your applications and the physical hardware. This is all about safe communication and control.
Now, we talk to the OS in a couple of different ways. Most of us, we use the graphical user interface, the GUI. That's your friendly windows, icons, menus, and your mouse pointer. But some folks prefer the command line interface, or CLI, which is a super powerful, direct way to tell the computer exactly what to do using text commands. But here's the thing, no matter how you talk to the OS, there is one golden rule that can never, ever be broken. Applications are not allowed to talk directly to the hardware. Ever. Just imagine if your web browser could decide to just start writing things to your hard drive whenever and wherever it wanted. It would be absolute chaos. So, what does an app do when it needs something that involves hardware? Well, it has to file a formal request with the manager. This is called a system call. It's basically the app raising its hand and saying, "Excuse me, Mr. Operating System, could you please do me a favor and save this file for me? Or could you please open up a network connection?"
And this diagram shows that process perfectly. You've got your application running over here in what's called user mode. That's a restricted, safe area with limited privileges. It needs to do something important, so it makes a system call. That call is like a special key that temporarily crosses a protective boundary into the all-powerful kernel mode. The OS in kernel mode carries out the request safely and then hands the result back. It's the ultimate gatekeeper.
Okay, this idea of user mode versus kernel mode, honestly, if you only take one thing away from all of this, this is it. The separation into two zones is the absolute foundation of all modern OS security and stability.
And to really understand why it's so important, let me ask you a question you've probably experienced yourself. How come when your video game crashes, you can just, force quit it and go on with your day? But when the operating system itself crashes, you get the blue screen of death and the entire computer grinds to a halt.
The answer is simple, but it's profound. They live in two completely different worlds. Your game lives out in the general population, in user space. But the core of the OS, the manager itself, lives in a protected fortress called kernel space.
And the difference in power between these two is just night and day. User space is where your apps run. They have very limited permissions. They're treated with suspicion. But kernel space, that's the control room. It's where the scheduler, the memory manager, all the device drivers live. It has total, complete, unrestricted control over every piece of hardware. So a crash in user space is just an isolated incident. A crash in kernel space, it's catastrophic.
It all boils down to a really simple rule, right? Your applications are like passengers on an airplane. You want them to have a good flight, but under no circumstances do you let them into the cockpit and start messing with the controls. The OS kernel is the pilot, and that separation is what keeps the whole plane flying safely.
Okay, but what about when the hardware needs to get the OS's attention? I mean, when you press a key on your keyboard, how does the CPU know it needs to stop what it's doing and pay attention? For that, it uses something called a hardware interrupt.
And the best way to think about this is to imagine you're studying. You're deep in concentration, reading a paragraph. That's the CPU chugging away on a task. Suddenly, someone calls your name. That's the keyboard sending an interrupt signal. You don't just throw your book away. You stop, you put a bookmark right where you were, you deal with the interruption, and then you come back to your book and pick up at the exact same word you left off on. That's precisely what the CPU does thousands of times a second.
All right, so let's quickly wrap this all up. The operating system is the essential manager for your computer. It uses the scheduler to create that amazing illusion of multitasking. It uses virtual memory to keep every application in its own safe, private workspace. It's built on two critical zones, the powerful, protected kernel space and the limited user space. And it forces apps to use system calls to ask for help, which keeps the entire system stable and secure.
And that leaves us with one last kind of mind-bending question to think about. If the operating system is the manager that starts up and controls everything else on the computer, what tiny, fundamental piece of code has to run first just to wake up the manager itself? But we'll save that one for another time. Thanks for joining me.